Hey everybody, I'm meteorologist Gavin Sandell. Well, before any weather we analyze on this segment happens, it's predicted through the use of weather models. That's a process us in the business call numerical weather prediction, and the topic that we'll take a deep dive into today. But before we can predict any weather, we need to actually figure out what the weather is, and there's a lot of ways that we could do that. The first one on the left is satellites, and these satellites are either polar orbiting or geostationary, which I'll talk about on Wednesday, but they uncover a world's amount of information from the surface to the oceans and up aloft as well. They're helped up by ground data as well. This instrument right here is called an ASOS station, which is typically at airports, and they can get different temperatures and dew points and other sorts of variables as well. These only come from the ground, but we can get stuff like weather balloons on this photo right here. This radiosonde picks up lots of different variables from the air as well, and with the help of aircraft as well, we can get really a 3D scope of what's going on weather-wise. So once we have all this information, we need to solve it, or basically figure out what the weather is going to be, right? So on the left side here, these are the equations that we use to actually get this. I'm sure you've never seen half of these letters or numbers that you see on here. Basically, what these equations are showing you is the change of a certain variable over a certain amount of time at a certain location. So, for example, this first one right here is the change in wind over a certain time, this being the horizontal wind and this being the vertical wind. Temperature as well, the change in temperature over a certain time as well. Basically, these equations are complicated, and in order to do that, we need the help of a supercomputer to do that. And even supercomputers have limits as well. So we basically divide the way that we model into two separate ways, and depending on what we want to get out of it. So on the left side, we're going to divide this into a large grid space. On the right side, we're going to divide this into a smaller grid space as well. Basically, the one on the right side, each grid space is 1/3 of the length and width shorter than the one on the left. So the left side we'll call global resolution, and because these points right here, these points that we solve different equations at, you have a point here, point here, point here, because there's less of them, we can get more room. There's 36 boxes across this map, and so we can have a larger range of times that we can set this for, because the computers are solving for less amounts of grid points. On the right side, we have what's called high resolution. So the computers are solving for a wide array of grid points, solving for separate locations. But what that does is it sacrifices time. So on the left side, we'll have a larger amount of time that we can solve these models for. But on the right side, we'll have a larger amount of resolution, and a lot of more local weather can be represented on the right side. So different types of models can be shown for either side. On the left side, you have the global forecast system, which we know as the GFS, or the European model, the ECMWF. These go for a very long time. These models go for 16 days for the GFS and 10 days for the European model, wide domain as well. But look at this resolution, on the sorts of 9 to 28 kilometers. Once you get to these shorter scale models, the HER or the NAM, this is the high resolution rapid refresh, and the North American mesoscale, you have a much shorter resolution, so you're getting a much more defined scale of what you're seeing, just 3 kilometers between those grid points, or you're solving the weather for 3 kilometers of space. The only thing, though, is you're sacrificing time, 2 days and 2.5 days. So these are different kinds of models that can help us in different sorts of ways as well. But another way that we can get helped by models is something called ensemble forecasting. And basically, instead of running the model once, we run it many different times. And the way that we can do that, or the way that it spits out different things, is we change the atmosphere just a little bit, because we're doing what's called parametrizing the atmosphere, or just assuming just a little bit, because we can't exactly figure out what the atmosphere is doing. So we're parametrizing it, and as a result, it expands a lot. So we get a lot of different model solutions in terms of ensemble forecasting. So with the help of better computing power, models have gotten much, much more reliable. The 7-day forecast we show you every day on WFMJ has become as reliable as what a 5-day forecast was in the year 2000. For Weather 101, I'm Gavin Sandell.